So I'm going to attempt to record a trial video by way of showing you more or less what I would like to see in some kind of a video effort, and also to work out an example from this current unit. So here goes. I've picked example 8, which we more or less did in class, and I recorded a video of me working it out, which I'll be starting and pausing from time to time and making comments about exactly what you're seeing. So here goes. It's going to start playing right now. Oh my goodness, I'm writing so fast. Okay, so for this example, so far what you can see is I've filled in some of the numbers and drawn a force diagram. Oh, let me back it up just a little bit. There we go. Distances I've filled in. You can see up here we've got 70 centimeters for the distance the cart travels, and 1.31 seconds is the time that it takes to go. In case you miss sort of the premise of it, right? We've got this hanging mass here, and it's pulling this cart along, and roughly speaking, we're pretending that it's entirely without friction, which is never completely true, but you've seen those wheels turn. They're pretty darn good. The weight that we've hung over here, it says, is 50 grams, which I converted over here into kilograms is 0.05. The weight doesn't simply fall, right? You can see right there it's got tension pulling upwards on it, gravity pulling down on it, and since the weight of that object is larger than the tension, it moves downwards. All right, since it's moving downwards, it's going to pull the cart to the right, and specifically the force that makes it do that is the tension. So as you can see, the normal force and the gravitational force here, those ones are all in the y direction and therefore don't affect motion unless there also happens to be friction involved, which we already said this is frictionless. All right, so there's our force diagram so far, and let's see how things go from here. All right. Next step, part B, you're supposed to write an equation that shows the sum of the forces. Let me pause for a moment here, and let's consider the one on the left. It says sum of the forces on little m, that would be the little hanging mass there, are given by mg minus t. All right, now you might expect that you'd be okay with writing like, say, t minus mg equals ma. All right, you might think, oh, it's not really going to matter whether, I put the tension first or the gravity first. Well, if you did it like that, you'd actually get the wrong answer. Your answer would be wrong because the larger force here is gravity. It's pulling the little mass down, and therefore the acceleration is going to be in the direction of that larger force. Therefore, you don't want the tension to be labeled as positive. You want gravity to be labeled as positive because that's the direction of the acceleration. All right, nope. All right, and then I'm going to delete my scrawl just there. Okay, let's continue playing this video. All right, now we're writing a equation for the sum of the forces acting on that cart. Now, if you look at what I've written there, we just have tension, right? There is no vertical forces listed in that equation because they don't affect horizontal motion. All right, and then I took this equation and that equation, and you can see what I did here is I added them together, and the tensions cancel. If you are working with a problem where one thing pulls another, the tensions should always cancel, and if they don't, it means that you screwed up. All right, let's play there we go. All right, now what I did there, let's see if we can pause it. Pause, good timing. All right, as you can see right here, I came up with an expression for the acceleration. Now that's something you'd want to do if you, say, knew both of the masses, and that was what it was asking for anyway. In this case, we actually don't know the mass of the larger cart, so what we're actually going to try and do is get an expression for the big M there. That's the mass of the cart. We'll have to find the acceleration another way. That's what's happening right over here. So holy cow, kinematics just came back into it, right? So we have 0.7. That's the displacement. Notice up here I gave it in centimeters, but you have to always convert to meters. And then we have time right there, so 1/2 AT squared because the initial velocity happened to be 0. All right, let's go ahead and start that up again and see what it does. Oh, typing things into my calculator. Okay, there we go. Acceleration is 0.816 meters per second squared. Rewriting the expression, solving for m. Plug in some numbers, and look at that. The mass is 0.55 kilograms. And there, finally, I'm drawing an arrow showing some of the things I'm plugging in, right? All right, yes, so A was 0.816, and that went over there. If you need to rework the algebra a little bit, solve for m yourself, you can take care of that on your own. Pause the video whenever you're ready to move forward. All right, let's keep going. Now we're going to move to part D. D is saying, look, we can change the angle of the track and figure out at what angle it's going to be able to remain stationary. Now let me actually back up that video a little bit because I don't want you guys to see everything too soon. Oh no, a little forward. Yeah, there, stop. Okay. As you can see, we've got tension upwards on that hanging mass and gravity down. That's no different, really, in terms of like which forces are acting on it. However, if we were to say solve for tension in the first part of the problem, we would find the tension is actually smaller than the weight of the object. If we come over here and look at this equation, right? If you solved for the tension, you would get T equals mg minus ma. Meaning the tension is not equal to the weight of the object. It has to be sort of adjusted by how much it's accelerating by. So the result there then is that the tension's not going to just equal the weight unless the acceleration is in fact 0. For part D, it's asking about what exactly is required in order to keep the mass at, keep the cart at equilibrium, which means now the acceleration will be 0, and therefore the tension just equals the weight. Okay, let me say that a different way. The tension only equals the weight of the object if it's just hanging there. If it's not just hanging, then the tension is going to be something different. The tension will be larger than the weight of the object if it's accelerating upwards, but the tension will be less than the weight of the object if the object is falling downwards. Okay, let me erase that right there, and let's carry on. What we're going to show next is sums of the forces acting on the various objects there. This one over here is different. It's going to be a different equation from what we have over there, right? This one, it was just tension equals mass times acceleration, because the only horizontal force, meaning the only force parallel to motion, was the tension. Over here, that's no longer going to be the case. We're going to have gravity is straight down, but since the incline is sloped, we're going to have to tilt our axes so that the x direction is now parallel to the incline. That's going to mean that gravity has a component parallel to the incline. We've drawn this triangle a bunch of times in class, right? So we are going to be looking for this side right here, right? And that's going to be related to the sine function. And what you'll see in a moment is that it is mg times sine theta. All right, let's play that video and see what happens. Here we go. Some of the forces on the little mass. Notice this time the sum of the forces is 0. That's because it's just hanging, right? It's in equilibrium. And there, like I said, we've got mg sine theta minus t, right, instead of just tension. All right, let's play, see what happens. Adding the two equations together, the tension cancels, and that 1/11 there, that's oh, I'm about to write it. That's the ratio of the masses. That's 0.05 divided by 0.55. And a better calculator says 5.22 degrees. Fine, there we go. Now, if a homework question were to ask you for the acceleration of something on an inclined plane in a situation like this, I'd like you to consider these equations over here would only actually be slightly different. Instead of 0, would have ma, and we might have to change the order of those two tensions, or excuse me, those two forces, but that would be about the extent of it, right? And same would be true here, right? But have to change those two, okay? So if there's acceleration, don't add them up to 0. It's going to add up to ma. All right, I hope that was informative and gave you some kind of an idea of the sort of thing that I'm looking for with your video project. Sorry, that was my son talking in the background. And I hope that it was helpful with regard to this current chapter as well. Thanks very much.